Okay, hello, can you hear me? Yeah. Hi, so I'm NADJA POPOVICH, and I'm a graphics editor on the climate team at the New York Times. And I want to take a minute just to explain what that means, because it's kind of a special team at the Times. So the climate team was formed last year. They brought together a group of journalists who are going to focus specifically on the topic of climate change and kind of related issues. And at the time, the Times wanted to make sure that this wasn't just a team of extremely talented writers, but also people who were visually focused and could tell the story of climate change in new ways. So this is just a few of the stories that have been done over the past year from the team, along with our friends in the broader graphics department. As you can see, it spans a lot of different kinds of things, everything from maps and charts and graphs to up here you have a still from a piece that was using drone footage to show how Easter Island is uniquely vulnerable to climate change. Over here, we took you under the ice in Antarctica for a VR project. And then it's even things like telling stories through GIFs. Like here you see a story that was actually about invasive python species in the Florida Everglades. So currently it's a team of about 12 people. That includes editors, writers, a graphics editor, me, and some multimedia folks. And on the team, my job specifically focuses on the aforementioned charts and graphs and maps. And generally, I do explanatory graphics. So that's what I'm going to talk a little bit about today. I want to kind of take you through the work that I do and talk about some of the goals and challenges of visualizing climate change. Okay, so to start, I kind of want to take you back to the basics. So it's getting hotter out, right? We know this. This is a chart from NOAA, which is the National Oceanic and Atmospheric Administration in the United States. It shows temperature anomalies over time. So that's basically how much warmer or cooler a year was compared to a baseline average, in this case, the 20th century. If you haven't seen this chart, you may have seen one of these. This is probably one of the most visualized data sets in climate change. All of these charts and graphs show basically the same idea, which is global temperature change over time. And it's everything from animations over time to these really nice kind of using color to show change over time. They're made by scientists and journalists and designers. And this is a really important data set, and it's also a living data set in climate change. It gets updated every year, and lately it also makes news every year as we continue to break records. So this is the earliest I could find it visualized in the New York Times. Here you see the planet warms. This is from 1995. An up-close version, so it's average world surface temperatures, 1856 to present. You see it again in 2010, slightly different form. And again in 2014, temperature anomalies over time with this nice map showing where was hotter and cooler that year. Then again in 2016, when for the third year in a row, we saw a temperature record. And this was a really nice chart done by my colleague Jugal Patel, who showed temperature anomalies by month over time. And so this past year, we got news from NASA that it actually wasn't going to be the fourth straight hottest year in a row, but it was still a very hot year. And I worked with a colleague of mine who was writing the piece to talk to the scientists really about okay, well, is there anything more that we can say about 2017? And the scientists were really focused on this fact that 2017, unlike some of the other previous years like 2016, was actually a year in which we didn't see an El Nino. So this is the specific cycle that basically boosts temperatures worldwide. And because it wasn't an El Nino year, in some ways 2017 was actually more interesting than 2016 for how warm it was. And so that's what the article is really going to focus on. And so this is what we did for it. Again, you see that nice change over time chart that shows it's getting warmer. And then there was this second step where you kind of receded the other years back and just showed those without El Nino. And this isn't like a super groundbreaking thing to add, right? But it does point to something we try to do really often with these kinds of graphics, which is give a really full visual takeaway for our readers. It's something my editor, Hannah Fairfield, calls the visual nut graph. And in journalism, a nut graph is a paragraph pretty high up in a story where you really sum up what the rest of the story is going to be about, so that readers, even if they don't go any further than that in a story, they still get the majority of what they need to know. Okay, another data set that is very often visualized in climate change is Arctic sea ice decline over time. So you see lots of different ways of doing that here, including down here there's some charts about ice thickness. Up there there's the Arctic and Antarctic. And then there's my personal favorite. Sound? Sound? No? Okay, there's really dramatic music that's supposed to accompany this, so this actually breaks a lot of the less is more rules of data viz, but I actually think it's a really effective visualization of what's going on here with summer sea ice minimum receding. And so this is what we did last year. I worked with my colleague Adam Pierce to create this chart. Kind of animates over time. So we did what the headline says there. We charted Arctic sea ice for nearly every day. Each line is a year. The animation really reinforces kind of the downward trend, and the colors also show change over time. And then we highlight 2017, which is the year we're concerned with. And you really see this trend going on for that year too. Up here is the it's the winter maximum, so that's like how high the ice gets in the winter, and so 2017 was the lowest winter maximum on record. And then you see it kind of fall towards the summer minimum, which is like how small the ice eventually gets. Oops. Okay, so another kind of piece that you see very often visualized in climate change, although not with charts and graphs usually, is glacier loss. So here you see things like this. This is Muir Glacier in Alaska in 1941, and then again in 2004. And these kind of photos really reinforce ice loss, right, and how the world has changed. So last year, the study came out from the United States Geologic Survey that showed, it looked at glacier loss in Glacier National Park, which is this pretty well-known national park in the United States. It's in Montana. It gets about 1 million visitors a year. And what was really interesting about this study is that they looked at 39 glaciers across the whole park. And as I was reading through it, I noticed that they said that they actually traced the outlines of each of the glaciers using satellite data and photos from back in the 60s. And so they had shapefiles for every single one of the glaciers over time. And I thought, well, wouldn't it be really interesting to take a look at all of the glaciers at once so that you could see both change for every individual glacier and also what's happening with the whole park. So this is what it came out like. You see there's like a 1966 footprint, so that's one of the shapefiles, and then I layered on top the 2015 area, and you can really get a sense of how a lot of these glaciers have receded over time. This is the piece itself, so you can see like more of the glaciers as it scrolls through. And I think, you know, this piece was particularly popular partially because I think it also helps localize climate change a little bit. Very often we talk about climate change and like ice melting in the Arctic, but this is a place that for many Americans who are reading the Times, they may have visited it. And you know, thinking about Glacier National Park losing all of its glaciers is like a particularly hard-hitting thing for a lot of people. But glacier loss is also not something that's just localized to Glacier National Park, so I just wanted to show quickly. This is here in Europe. So in Switzerland, they've actually taken to tucking their glaciers in under these big tarps during the summer. They're reflective, and it's supposed to slow the melt of the glaciers. And so that brings me to kind of challenge number 2, and that is, you know, some of my favorite pieces that I've worked on over the past year have to do with going a little bit deeper into the impacts of climate change. And this often requires reading through scientific studies and pulling out some findings and then presenting them to a general audience. And so I know it's like rainy and cold here right now, but I want to take you back to last summer when across Europe we saw rolling heat waves, including one that was so hot it was nicknamed Lucifer. In Iran, we saw some of the hottest temperatures ever recorded on Earth, and in the US West Coast, it was so hot at one point that in Phoenix, planes couldn't take off and land. And whenever we see these kinds of extreme events, this question often comes up, which is, is this normal? Is this just a heat wave? Or is this climate change? And scientists have lots of different ways of answering this question. They now do attribution studies of individual heat waves. But at the time, I really wanted to take kind of a broader look at this question. So I read through a bunch of studies and ended up finding one that had this visual in it that I just really loved. So this chart shows basically what it says up there. It's the shifting distribution of temperature anomalies in the northern hemisphere land in June, July, and August, which is summer. And so under this curve here, so this is the base period, 1951 to 80. Under the curve, you see temperature anomalies at gridded locations across the northern hemisphere. And what the researchers did, essentially, is sort of define them in these ranges. The middle 30% of temperatures at that time were classified as being normal. The next third were hot, and then on the other side, the blue is cold. And then in the wings, so past 3 standard deviations, you really see extremely hot and extremely cold temperatures. And there's not a lot of those in that base period. And then over time, for the subsequent 10-year periods, you see the temperatures compared to the base period begin to shift over. And you see a lot more temperatures end up in that hot and extremely hot category. And the reason I thought this was so great as an explanatory chart is because it really gets to something that's a pretty basic idea in climate change, and that is that small changes in temperature average, so it's only gotten a little bit hotter over these like 50 plus years, even those can lead to pretty big changes in the extremes. And so one thing I needed to do in order to present this to our audience is simplify it a little bit. I think if I showed someone who probably has less of a stats background, something like local standard deviations as an x-axis, they probably wouldn't quite know what I'm talking about. So in the end, this is what I ended up making with my colleague Adam Pierce again. It's very similar. It keeps some of the best parts of that previous visualization. But as you can see, the x-axis here just becomes those categories that the researchers themselves defined. The y-axis is simplified just to say more frequent. And we animated it over time to really reinforce that shift. And I think people reacted pretty well to this. It was another pretty popular piece. We got a lot of really good feedback. And then we also got a little bit of this. So, it's not getting hotter here, or I'm cold right now. And I don't put this up to poke fun or be like climate versus weather. But I think it does show a pretty big challenge of communicating climate change. And that's that we're often talking about averages, big averages over 30-year periods, over the northern hemisphere. And I think people just find that a little bit hard to relate to. So I spend a lot of time thinking about how to make this stuff more relatable. And one way to do that is with maps. So in the winter, when something like this came up again and we wanted to look at, so the US had a pretty abnormally warm winter, and again it was well, is this normal? So with another colleague, I took temperature anomaly data from NOAA and we made these maps showing in the US how winters have warmed up. And the US is just a small part of the world, and usually we talk about global warming as the world, but it's a big enough land area that you can still talk about some of these patterns. And as you can see, that last 30-year period really is a lot redder, it's a lot warmer. But also you start to see some nice geographic patterns emerge, right? You see up there where, so that's the upper Great Plains, so Minnesota, Montana, the Dakotas, warmed a lot faster than the rest of the United States in the winter. And then some parts of the Southeast didn't actually maybe warm that much at all compared to the rest of the country. And so people get to kind of see that this isn't evenly distributed everywhere, and it gives you a little bit of a better idea. But it's not just science in climate change that usually needs translating. Some of the policy behind it is pretty complex too. And so I don't know how many of you here have heard of the Paris Agreement, but for those of you who haven't, it was basically this big international accord where the US and China and France and other European countries and like over 100 countries around the world got together and they said, we're gonna work to limit emissions to keep warming below 2 degrees of Celsius. And we're gonna make our best effort to keep it below 1.5 degrees. And since this, so this was all in 2015, since this, our government has changed administrations and our current president has said he's gonna pull the United States out of the Paris Agreement. But that's actually a pretty long process. And I'm actually not gonna go into it. All you need to know is that there was another climate conference this year that you probably heard less about. It was in Bonn, Germany. And this is where all the countries got together and said, basically, we need to hammer out some of the details about the Paris Agreement. So accountability measures, things like that. And ahead of this, my colleague Brad Plumer and I wanted to take a look at okay, it's been 2 years since the Paris Agreement. There's this big conference where they were talking about accountability measures. Is there any way to tell how countries are doing so far? Are they on the way to meeting their Paris goals? And lucky for us, there's someone who keeps this data. So this comes from the Climate Action Tracker. And it's a really great tool, especially if you're a journalist who's trying to answer the question of where countries are standing. But I think it's a pretty dense chart to come to if you're someone who doesn't really know anything about this. So looking at this, I wanted to really break it down into its component parts. And so what are those? Over here, the black line, you see historical emissions. Then after that, there's really 3 parts. One, current emissions. So that's kind of the blue line and the dotted ones. Then there's the Paris pledges, which are the black dots. And then these red to green colored areas are actually the ranges you would need to hit if you wanted to actually stay below certain degrees of warming according to this group. So red is 4 degrees, orange is 3, and so on. And so when I was thinking of what do we do with this, I thought those are really the 3 things that I wanted to walk our readers through. So this is what I ended up making. It's a pretty simple chart, but it uses conversational language on top of it to really reinforce what you're looking at here, so you're not kind of guessing, because this is all pretty abstract in the first place, right? So this is the United States. So it basically says this is our estimated current emissions trajectory. And then here's what we pledged under the Paris Agreement. And then this is what would actually be needed for 2 degrees. And so I made one of these charts for this is the world, and then 4 other countries. And each of them follow this 3-step progression that I think is really important here, because especially okay, for the United States, maybe you see, oh, okay, we're not quite reading our trajectory, but then there's this kind of surprising third moment of most countries, so even the European Union, which actually is kind of meeting its trajectory, this is what 2 degrees would look like, right? And so it shows how much further a lot of the world has to work in order to actually meet the goals of the Paris Agreement and not just what they've kind of been working on so far. And so that set of charts really sets us up well for the last piece that I want to talk about, which is one of the big challenges of visualizing climate change is visualizing the future. So a lot of the data that I've shown so far, except for that past chart, was observational data, right? It's getting hotter because we've measured it. Sea ice, it's the satellite record. But quite often, we also need to visualize the future. So I wanted to start this section with this nice quote from some some scientists who work on climate change. So they say, if we had observations of the future, we obviously would trust them more than models, but unfortunately, observations of the future are not available at this time. And so that kind of applies to my job too. If I had observations of the future, I would obviously visualize that data, but I don't, so I am often working with models. And here's one example of that. So this is a piece where a colleague of mine, again, Brad Plumer, worked on this piece looking at 95-degree days and how they're going to spread across the world, or how they could spread across the world, could being the key word here. And when we got this data from the scientists, they gave us 2 emissions pathways. So you might be wondering, what are emissions pathways? And basically, one of the big uncertainties of climate change is us humans, so how much we're going to emit in the future. That's something that in a lot of studies like this one, climate scientists don't actually try to predict. They don't try to predict how much more we're going to emit in the future, because it's quite complicated. It has to do with population growth and economic growth. And instead, they use one of these kind of set emissions pathways. And there's 4 of these, really high emissions, so like what if we emitted a lot of more CO2, a low emissions pathway, and then kind of 2 in between. And they plug these into the models to see how the system will react. And so in this case, like I said, they gave us 2 of these. And I thought a lot about how to visualize that, right? Like, would we show 2 different scenarios and give people toggle buttons where they can toggle between scenarios and between years? But that just seemed like possibly more confusing than it was actually telling you very much about this story. And so Brad and I decided that instead we would really weave both emission scenarios into a narrative. And so this first one is kind of explained in the paragraph right below it, where we say this is a scenario where countries would take some measures but not drastic ones to curb emissions. And then further down in the piece, we put up a second scenario, which is this one over here. So things could get worse if countries fail to take action. And these are actually kind of, scrolled through, but I wanted to put them next to each other because I think it's really interesting to look at them together. So, for sure the patterns of warming are the same. So, why show both? And I think one of the reasons is that really, especially by that end period, so 2080 to 2099, you kind of see this big difference in how much hotter it's going to get, or how many more of these like extremely hot, like sweltering days you're going to get around the world. But also I think that showing both scenarios kind of helps hint at this uncertainty again, right? Like, we don't know how much more we're going to emit, and there are multiple plausible pathways forward. But of course, this isn't the only kind of uncertainty that we visualize in climate change. So I did not do this. This is a map from the FT that I thought was just really nice. And it visualizes a different kind of uncertainty, which is confidence. So it shows New Jersey coastal properties under threat from flooding. And then it has these kind of 3 different scenarios. So if sea level rises by 2 feet, if it rises by 4, or by 6 feet. And the blue areas are flooding confidence high. And so what that means basically here is that 8 out of 10 times the models agree that these areas are going to be flooded. And then the purple parts are ones where some models think it's going to flood there, others maybe don't. Or sorry, some forecasts think it's going to flood there, some don't. But there's still a risk of flooding. And I think this just does a really nice job, again, of kind of visually hinting at this idea that we don't know exactly what's going to happen in the future, but both of these areas are potentially at risk. And to end, I just wanted to show one more piece that isn't mine, but is actually by The Guardian. It's this piece called The 3-Degree World, the cities that will be drowned by global warming. So I thought this was just a really nice piece. It was mostly about sea level rise, but my favorite graphic in it was actually this graphic that they put on top, which explained where they got this 3-degree number from. So this is what the graphic looked like. And like I was talking about before about scenarios, this is actually from a study that does try to predict how much more we're going to emit. So the study used some fairly new UN projections on population growth and decided to run those through a climate model. And there's a lot of uncertainty still involved, both in how population is going to grow and how development is going to go, and then also there's uncertainty in the physical system reactions. But I think you really get to see something here that is really nice, and that is you get to see how each projection, so this is one projection, comes out, and then you see some possible worlds in which we end up down here at like 1 degree of warming. then there's some possible worlds in which we end up way up above 5 degrees Celsius of warming. But most of these projections really cluster in around this 2 to 4 degree area. And then they draw in the average, which leads you to 3 degrees. And I think, as a reader, putting this at the beginning of the article really allows me to understand much more deeply what we're talking about here. It's not like scientists magically pulled the number 3 degrees out of a hat. They just ran this kind of model, and then you see where 3 degrees comes from. And I think this piece, like the 2 others I showed before, does something quite nice, which is it gives readers just a little bit more information. It takes them a little bit more behind the science, and in that way it really deepens their knowledge. And these are the kinds of projects I hope to work a lot more in the next year. Thank you.